Okay, now we're ready to solve the remaining problem. And the remaining problem is out of chapter 8, 8131. It is the ideal Erikson cycle, operating as the ideal Erikson cycle. And it's number or letter OKE. And so in this particular problem, we have kind of some unique conditions associated with the compressor and the turbine. We find that the Erikson cycle assumes a constant temperature compression event, and the constant temperature, the heat that's rejected, is being rejected at a temperature of 30 degrees Celsius, which happens to be the incoming temperature associated with state 3. The incoming pressure is 115 kPa. And so state 4 is at the same temperature. And what we assume is during the compression process, there is a rejection of heat. That rejection of heat is reversible in nature. It occurs at a constant temperature to a constant temperature reservoir, and the amount of rejected heat is 155 kilojoules per kilogram. We also know over on the turbine side that the expansion from 1 to 2 is also constant temperature, and the temperature there, so temperature 1 and temperature 2 are both at the temperature that the heat transfer to the air occurs, at 1250. So we have 1250, and that is the temperature that is coming in, added to the system, added to that particular expansion process. And so our temperature at 1 and 2 is 1250. It is a constant temperature process, and the heat transfer that's occurring there into the system will be able to be calculated. Okay, and then we have this regenerator, and what happens is the regenerator is just a heat exchanger, and we know the incoming temperature of one stream is 1250, and it drops to the 30 degrees through this process, whereas the fluid in the other path is going from 30 degrees up to 250. And so basically with perfect gas, a perfect gas model, we have the same delta T associated with the fluids as they exchange their enthalpy. And so we actually won't have to set up a device panel for that because we already know all 4 temperatures. We also know once we determine the pressure, for the compressor, we'll also be able to determine the pressure associated with the turbine expansion. Okay, so in fact, we have a known pressure here, and state 4 is going to be an elevated pressure. And then we also, at state 3, that pressure is the same as at state 2. And so the expansion starts at some unknown value of pressure. And it turns out that that unknown value of pressure is actually tied to state 4. And so in essence, once we figure out for the heat transfer that is going in to the compressor, that's going to give us all the pressure conditions, we know the temperature conditions, and so all the pressures and the temperatures will then be established. And so they're asking us for what's the maximum pressure in the cycle, and the maximum pressure in the cycle is going to be whatever we determine 4 to be, and that's also the pressure at 1. They're asking us for the net work output per mass of air, as well as the thermal efficiency of the cycle. So with that in mind, we got to have a little bit of different nomenclature here. We can start off, if we wanted to, with the turbine from 1 to 2, and then the compressor from 3 to 4. But since we know the heat transfer that's occurring at this compressor, we'll go ahead and work with this side to begin with. And so we go into our test apps. And this is a gas power cycle, a flowing system. And so we select that. Air is our working fluid. We're going to assume it's a perfect gas. And we'll then go to our test app. So in this particular problem, we don't have to concern ourselves with any exergy because they didn't ask us for anything. So we don't have to set up a dead state. I'm going to go ahead and jump over to state 3 where we know information. We know that the pressure is 115 kPa as given in the problem, and we also know that the incoming temperature is 30 degrees. Now, in this particular case, because we're looking for the net work output per unit mass, and since this is a flowing system, I'm going to go ahead and set the m dot equal to 1 for m dot 3. And what this will allow us to do then is in our device panels and our cycle panels, anytime we see, we will be able to see kilowatts as power instead of dealing with work on a per mass basis. And so the two are interchangeable is what I'm trying to say. Okay, so we have state 3 identified, and let's go ahead, and what we know about state 4 is the temperature stays the same. And so I can say that this is equal to temperature 3. We also know that the m dot is the same as m dot 3, and it's going through this constant pressure turbine process. And it's not isentropic. And so in order to calculate the pressure, we're going to go right away to the device panel. And the device panel, will go from 3 to 4. And what we know about this device, this constant temperature compression, is that the heat transfer is coming from a temperature of 30 degrees. So that is our boundary temperature. Now, because we know the Q dot, we know that the Q dot for this is a rejected minus 155. Okay, so as soon as we put in minus 155, it was able, through the first law, since the temperature is the same, this term goes to 0. And we just have heat transfer is equal to work. Now, we also know that in this particular case, because it's reversible heat transfer at constant temperature, we also know that S dot is equal to 0. And so the entropy balance equation with Sgen equal to 0 basically is what related then the entropy change. And there is an entropy change not because temperature went up, because temperature stayed the same, but pressure changed. And then we have the heat transfer divided by the temperature that the heat transfer occurred from. And so we have everything that we needed then for state 4. And so we see that it calculates the entropy value and it calculates the pressure associated with that exit of the compressor. And so we know the temperature and the pressure at the exit. And so that then allows us to now go over to the turbine, because now we know for the turbine, state 1 corresponds to that same pressure. So state 1 is pressure 4. Okay, it went through that heat exchanger, but with no pressure change. What else do we know about state 1? We know that the temperature at state 1 is in Kelvin, it's 1250 Kelvin. We also know that the m dot is equal to the same as m dot 3, as we set up before. And so now we know all the thermodynamic conditions associated with the incoming flow of that constant temperature turbine. We now can go to state 2, which is the out value, and we know that the pressure drops to the pressure at P3, which is the 115 kPa. We also know that the outlet of the turbine is at the same temperature as the inlet of the turbine, and we know that the m dot is equal to 3. M dot 3. So we have all of the state points. If we looked at that on the graphics panel, we have, the two conditions here. We have we start off with the incoming at 3. We compress it at a constant temperature to a lower entropy value because pressure has that effect. As pressure goes up, constant temperature, and then from 4 to 1 we have just a constant pressure process as we go through the heat exchanger to state 1. And if I were to put a constant pressure line through state 4, that's that one side of the heat exchanger. If I go to state 2, I can put a constant pressure line through that. And then I have these constant temperature lines that I can also put in. Here's the constant temperature at the 1250, and I can go down to state 3 and put in the constant temperature at 30 degrees there. So that's the diagram for this Ericsson cycle. Now, what does the Ericsson cycle basically tell us? The Ericsson cycle basically says that any heat transfer between 2 and 3 is actually transferred, from 1 to 4. Or saying that the other way, 2 to 3. 2 to 3 is the heat as we go through that heat exchanger from 2 to 3. We have heat transfer leaving the system going into the rise of temperature between 4 and 1. And so there's a regenerative nature between those two. And then the heat transfers between 3 and 4 and 1 and 2 are just the reversible heat transfers, either rejected in the compressor or added in the turbine. And the magnitudes of those two heat transfers, because it's reversible, is just the area under the TS diagram. And so for the compressor, the area between these two entropies and the temperature is the minus 155 as we went from 3 to 4. And so it calculated that fourth entropy, state 4 entropy, because we put in the heat transfer. Likewise, over here between 1 and 2, the heat that we add to the system is going to be that area. Okay, so we haven't actually put in the device panel, the second device panel, which is between 1 and 2. 1 and 2. And again, what we know about between 1 and 2 is we know that it's reversibly done. And what you see happening here is it doesn't solve for Q or the heat transfer of the work. But if you come over here, what you do know that the heat transfer or the work associated with that turbine is equal to the heat transfer. Okay, and you know that because of the energy balance. Because it's constant temperature, you know that the heat transfer and the work are the same. And so I could actually put in here Q dot 2. And upon doing that and calculating it, it then calculated what that heat transfer was. Okay. Now, before doing that, if I left that undone and I left that undone, this is where we were at. Now, what I haven't done yet, and this is important, is I needed to make sure I added the right temperature, and that's this temperature here, because we know that the entropy change, when this term is equal to 0, the entropy change is related to the heat transfer and the boundary temperature. And so our boundary temperature is 1250 Kelvin. Now again, it doesn't fill this in even when you hit calculate, even if you hit super calculate, but it's actually there. If you would click on it and then, see that and then do this, then it actually shows up. And so I'm not really sure why the software doesn't show it to you. And so there are a number of different ways to get to it. One of the ways I just discovered was, clicking on one of the things and then you see it and allow it to stay there. Another way is that you can actually set this equal to this Q.2 and then it would calculate it. You could also put in the m dot, the flow rate, times the temperature times the difference in the entropy. You could actually put in the equation representing that heat transfer given by that area right there. So with that in mind, we now have the heat transfer. We have the heat transfer that was rejected. We have the heat transfer that was added to the system. We go to our cycle panel and we see here's the rejected amount of heat transfer. Here is the added heat transfer. The net heat transfer is this. Here is the work out. Here is the compression work. Here is the net work. And so the thermal efficiency is simply 484 divided by 639. And that shows up here as 75.7%. It also asks for the maximum pressure in the cycle. And the maximum pressure in the cycle shows up here as 682 kPa. And it asks for the net work output per unit mass. And that basically, even though this is in kilowatts, we know that this was generated for a 1 kilogram per second mass flow rate. And so this is also 484 kilojoules per kilogram of mass through the system. Okay. Now, a final note is that this Ericsson cycle, because of the constant temperature heat additions and the regeneration that we see within the cycle, the Ericsson cycle actually approaches or has the same thermal efficiency as the Carnot cycle. And the Carnot cycle's efficiency shown here is simply 1 minus, and you can see it, let's see, they don't have it here. It's actually, this Carnot efficiency is actually 1 minus the low temperature in the system divided by the max temperature. And so that's why they're showing you the max and the min. And so when you take 303 divided by 1250, take that ratio and subtract it from 1, you get about 75%. And so we got the same thermal efficiency because this is acting because of the reversible nature of the heat transfers operating between the two temperatures. It's acting as if it was a Carnot reversible power cycle. And with that, I'm going to turn off